it up so it automatically records. There we go. Thank you very, very much. So, yep, we're now recording. Okay, so we're going to do 13.4, which is motion in space with velocity and acceleration. Before we do this, let's back up and let's make sure we understand how to do a tangent and a normal vector. All right, so, whoopsie, because as the feedback indicated, and my worry is I lost the, turn the chat on over here. I lost the forest between the trees. And this is much more of a type of problem you'll see on an exam. All right, so if we're given something like this, right? And that is our R vector. Now, let's remember what that R vector tells us. That R vector tells us, it's giving us an idea, right? And I'm just going to draw it in 2D. But if this is my R vector, and this is actually was a great discussion we had yesterday in office hours. If this is my R vector, what's going to happen is it's going to move with time. And this goes into your project. So at t equals 0, right, it might be here. At t equals 10, it might be hanging out over there. Okay, so it's what that R vector is doing is as you're changing time, it's tracing a path through the universe. The reason why this will come into the project you're going to do is if you're going to, and by the way, your project's in 2D, if you're going to spell out a word using a welding robot, which is your project, at different times you're going to want different vectors to be able to describe that word. Okay, so slight tangent, sorry about that. Let's go ahead and do real tangent. All right, so if we want to find the tangent vector at any point, all right, what's that going to be then? That's then going to be the derivative of the position vector divided by, no, it's not a square root, divided by the magnitude of the position vector, okay? Sometimes you're given a point, which allows these to fall out pretty nice or sweet. Sometimes you're not. This one's actually going to work for us. Oh, you guys are talking about the Discord thing. So I'm going to ignore that because I was talking about the project. No, the project's not an app. You have to do it. All right. So, oh, don't apologize. I'm glad you guys are working together and you're working with each other because that's the best way to learn. All right, the normal vector, and this was a discussion of a Chegg screen, right? The normal vector, that's then the derivative of the tangent vector over the normal of, or not the normal, but the magnitude of our derivative of our tangent vector. So I know if you look the problem up I was doing in class, and it's the same problem in your homework, and you go to Chegg and you look it up, they just sort of, it magically appears, okay? There is some work in there, and I don't know why they just had it magically appear. Well, they did because they were lazy. They plugged it into a program like Wolfram Alpha, which took the derivative for them, and said, poof, here it is, we're all good. All right, so let's go ahead. Our R vector is then t, 3 cosine t, 3 sine t, all right.
Shouldn't it be
Derivative of this, what, is there a question? Okay, I thought I heard something. The derivative of this, when we take the derivative of t, that's just going to be 1. Then we're going to have what? Negative 3 sine t, and then we're going to have positive 3 cosine t. All right?
Will you go back up to the top?
Sure. Yes, Eric, this is a new problem. Oh, you know what? I wrote down the derivative. I'm sorry. Let me write down the original problem.
Thank you.
Yeah, yeah. my bad. So this should be 3, let's do the original problem, cosine t, 3 sine of t.
And wasn't that 1 a t in the original?
And this should be a t in the original, yes. Okay, so use this as the original problem, not what I initially wrote down. All right, just as a reminder, I'm saying this out loud for me more than you, I will get the Dropbox. In fact, I'll just do it before I leave today. Dropbox is on, Dropbox is for the social dilemma. And I don't know with like the group app that Joe was sharing, if you guys can screen share in that, and then maybe one person who has Netflix access, everyone can sit and watch it together. Okay, yeah, feel free to do a viewing party for that one. All right, so are we comfortable? I keep getting distracted today. Are we comfortable with how we got this derivative? All good? You guys are working as a class. It's for educational purposes. Okay, so let's go ahead then and let's look at what's going to happen with the magnitude. And as I said, this is closer to what you'll see on an exam. This is going to be the square root of 1 squared plus -3 sine t squared plus, this is then going to be +3 cosine t squared. So that's then going to end up to be the square root of 1 plus, now what's going to happen here? This is going to become 9 sine squared of t. This is going to become 9 cosine squared of t. I can then do what? If I factor that 9 out, sine squared of t plus cosine of squared of t, right? That's going to become 1. I told you the answer. I meant to say, what's that going to become? But that's going to become 1. So then we're going to have the square root of 1 plus 9, which then gives me the square root of 10. All right. We doing okay, Joe?
Did you just see it, the wheels turning? Can you just go up a little bit?
Sure, be happy to.
Okay.
Yeah.
Thanks.
Is that where you need to be?
Okay.
Yeah. Thanks.
So let me go when we're ready to continue. Okay. All right. So this one ends up being really nice, isn't it? Because it's just a number. Okay, so when we're dealing with the sines and the cosines, things are much cleaner than when we're dealing with those e values. All right, so I then have, I'm sorry. All right, so we end up then with what? We then end up with our tangent vector, right? It's equal then 1 over the square root of 10. This is a 1, -3 sine of t positive 3 cosine t. All right. Okay, now that 1 over the square root of 10, that's just going to hang out there. Now let's talk about finding our normal vector. All right, so once again, the normal vector that's then what? That's going to be the derivative of the tangent vector divided by the magnitude of the derivative of the tangent vector. All right. So let's go ahead and find the derivative then of this. The 1 over the square root of 10, he's just going to hang out front. The derivative of 1 is then going to be 0. The derivative of the negative 3 sine of t is then going to be negative 3 cosine of t. And then the 3 cosine of t is then going to be negative 3 sine of t. Is that correct, folks?
Yes.
Thank you. I don't know why that doesn't work in my brain, but it doesn't. I would always write that down on my scratch paper, those two, before I started a test, because I just couldn't seem to get it to learn it. All right. So let's go ahead then. And as you can see, this is a much easier, equation to work with. All right. Once again, when we find the magnitude then of the derivative.
Quick question.
Yeah.
Why do we ignore the 1 over square root of 10 if that entire thing is the tangent vector?
Because it's just a constant. Like if I have 2t and there's a constant out front of the t and I take the derivative, the constant just hangs out.
Gotcha.
So I just left the constant hanging out.
Okay, thank you.
You're welcome. Okay, so if we think about, we can go ahead, let's go ahead and distribute that back through, because that might help. Let's go ahead and distribute that guy in when you see how to do the magnitude. All right, 0, it doesn't matter. This is then going to be negative 3 cosine t over square root of 10, and this is then going to be negative 3 sine of t over the square root of 10. All right, so now let's go after, whoopsie, I'm sorry about that. Now let's go after our magnitude. We're then going to have 0 plus negative 3 cosine of t over the square root of 10, quantity squared, plus negative 3 sine of t over the square root of 10, quantity squared.
Also, would you mind letting Ethan into the into the class?
I did. I did let him in.
Yeah, I'm in here.
Yeah, he's right there. I let him in. I let him in as soon as it popped up. So good to have you with us today, Ethan. Okay. So this becomes 0, 9 cosine squared of t over 10. And then we have 9 sine squared of t over 10. Right? Once again, I can factor out 9 over 10, and that leaves me then with cosine squared of t plus sine squared of t. Right? This guy goes to what? He goes to 1. Maybe pause for a minute. That felt like it was going quick. All right. And so what do we end up with then? We end up with the square root of 9 over 10, or 3 over the square root of 10.
For the exam, do you care which way we enter our answer?
No. What I do care about is showing me logical work. If there's no work on the exam, you get no credit for it, okay? Because I can't, you know, I'm not, you know, if you guys are looking problems up on another device that's out of the camera range, don't do it. Because if I see it, then I'm gonna have to fail you. But if that, something like that's going on, and I've had that in the past, then, you know, you guys don't, no system is perfect. This is the system we're with at the moment. So don't do it. But if I don't have your work written out in detail, and I'll give you plenty of time on the exams, we're not gonna do exam during class time. I will have it open for probably at least 48 hours. If you need me to have it open for 72 hours, it's fine. And I'll give you double the amount of time you're gonna need. So I'll give you 4 hours to take the exam. Okay, I'm flexible about that, but I wanna see all your written work. Okay, so we're now able to write out our normal vector. Yeah, if it's, this class runs an hour, this class runs almost 2 hours. Okay, it technically is an hour, 45 minutes, or 40 minutes or something. I don't know, an hour, 40 minutes, you get a 10-minute break. I don't know, I don't remember. But this class runs close to 2 hours. So if we were in a normal classroom setting, you had 2 hours to take the exam, I said I would double it. So it gives you extra time to write all your work out. That's the key. All right. Okay. So I really need to finish this problem. So we're gonna have 1 over the square root of 10, and then this is 0, -3 cosine of t, -3 sine of t. All right. And then down here, I'm then going to have 3 over the square root of 10. So what ends up happening is those 10s go away, and we end up with then 1/3, 0, -3 cosine t, and then we'll have 3 sine of t. All right, so if I distribute this through, we'll end up with a 0, negative cosine t. Oh, and there's a negative here, negative sine of t. Okay. Actually, Hannah, I don't think that's that generous of me. I always do that. Don't I always do that? Yeah, I always do that. Well, maybe not for Calc 1, because we had so much time in there. But my Calc 2, Calc 3s, and DiffyQ classes, I reserve the room in such a way that I can I can pull a half hour on either end. But since this will be kind of open to you within, as I said, either a 48 or a 72-hour period, you know, if you need to take it at 6 in the morning when your kids are asleep, you can take it at 6 in the morning when the kids are asleep. All right, so let me know in the chat, how is this doing? Is this making a little bit more sense and working a little bit better now that we've done kind of a more straightforward one? Okay. I also want to give you time to scan in your work and get it to me, which is the other thing. I can't give you partial credit if I don't have work, and that's always been my argument in the past, but this semester, if you don't have work, then you don't get credit for the problem. And the work has to make sense. You just can't randomly write stuff down. All right, the rest of you, is this problem making more sense? Yeah, well, as I said, I was worried I lost you between the trees on that E example. Okay. All right, and you don't have an E example, hang on, you don't have an E example on your homework, or you have an E problem on your homework, which is why I did it. If you want to put it, as I said, into a Wolfram alpha type scenario, I'm not gonna, I'm not worried too much about it. You know, we kind of worked through it and you saw how it needed to happen, all right? Talking about the homework, I'm thinking, you have one problem on torsion, is that right? Is the last problem on torsion? Who's done the homework?
There's a couple
Yeah,
of
the last
examples
one
with
is
the
a
E.
torsion problem.
Yeah.
Okay, so there's a couple of examples with the E. The last problem is torsion. So let me make sure you have the equation for torsion.
They give it to us in the problem.
Okay, what's up, Ethan?
They give us the formula in the problem.
Okay, okay.
That one was fine.
So that one's okay. They give you the formula in the problem. And as I said, with some of these crazy E ones, I didn't see too many, guys.
There's a pretty
Number
gnarly
5,
one.
it's, yeah.
I see number 6.
Yeah, number 6. If we could do that one, that was not.
No, we did that one we tried that one on
Okay.
Wednesday. I'm not doing that one again.
I don't blame you.
Yeah.
Number
The on
9 has-
13.4, number 5, it's another one.
Yeah, but number 5 is an integration one. Oh, 5 is sine. Okay, see, that's weird. I got sines and cosines for number 5. So it fell out just like the one I did for you. How strange. So let's just really quickly make sure you have in your notes, and they give it to you and in the homework, but this is something you will need in the future. Okay, and that is torsion. And let's just talk about it. And it kind of leads us nicely into the next section. Okay. So when you're in your mechanical or dynamics or your engineering classes and you guys start talking, and I believe, hang on, I'm looking at my work. Give me a second. I believe that this here is a prime. Okay. All right, but they do give you, but let's sort of talk about this from a sort of a big picture standpoint. Right? Okay, because what's going on here is we're getting what? We're going to get a vector that comes out of here, aren't we? So, and this is what we're moving into. Right? We have a path of we have a scenario happening. Right? We have the position, and then we have the we then have the velocity vector, which is what's going on here. Okay, that's our, well, that's our second, our first one is the velocity. First one is the velocity. All right, the second derivative, okay, and let's see, let's call it that one there, right? That's gonna then be basically my acceleration vector. Now, that's why the torsion is why in the past I would always teach the binormal vector, because that's kind of physically what it is. Okay, so what you have here then is you're going to do a cross product between your acceleration and your velocity vectors, right? And then you're going to look at that third derivative. So the first derivative we know is velocity, correct? The second derivative of the position vector is acceleration. The third derivative of that position vector is what's called jerk. Okay, and so that's what you're looking at. Torsion is what? Torsion is a velocity, but it's a twisting motion. Okay, so how much can you twist something before it breaks? That's going to be your torsion equation. So if you think about it, when you're looking at it, you're twisting it and how fast you're twisting it, and then the initial jerk, how hard you're twisting it, is then going to tell you, is going to give you the torsion. You can think of it as if you're unscrewing the top of a bottle, right? You're using torsion to be able to do that. So I just wanted to give you the big picture relationship of it. Your last homework problem is a torsion problem, but it's not on your quiz, but I wanted to make sure that you saw it.
It is going to be a constant, what you were going to get at the end?
Right, you're going to come out with a number, okay? Because this gives you a vector, or let's call it a vector x. So when you take the dot product of two vectors, that's just going to be a number or a scalar over the magnitude, which is also a number or a scalar. So torsion is strictly, as I said, is strictly going to be that's going to be a scalar component. There isn't any direction to it. Okay. All right. So this, as I said, led us into what we're going to do today when we look at position and velocity and acceleration vectors. All right, the position vector, I'm just going to write these down real quick for you. All right, so the position vector we know very well, right? That's our R vector. Velocity vector is then going to be the derivative of the position vector, which is something you all did back when you took physics, if you haven't taken it yet. But if you're given an equation for the position, you take the derivative and then you get your equation for your velocity. In this case, right, they're going to be vectors. The acceleration, that's then going to be the derivative of the velocity, or it's then the second derivative of the position vector. Right? Acceleration is a vector, can be a vector. I don't know why you were told it was a constant, but it can be a vector. And then, as I mentioned, and you're not going to do any calculations with this in this class, if we have the third derivative, that's what? You can think of it as that's the change in the acceleration with respect to time, and that, believe it or not, is called jerk. Okay? Now, velocity is a vector. Speed is something we talk a lot about, right? And speed and velocity and now are going to be different because velocity is now going, or speed is now going to be the magnitude of the velocity. And I don't know, I like to think the best of people. So maybe what he was trying to tell you is the fact that speed is never a vector, okay? Because speed doesn't have direction. So speed will also just be a scalar unit or a number.
But jerk is its own thing.
Okay, I'm sorry, can you say that again?
Jerk is its own thing.
Yes, jerk is its own thing.
Mm.
Okay, and where you're going to see jerk is probably your junior, maybe even your senior level engineering courses, your advanced dynamics and mechanics courses. But yeah, jerk is its own thing. I mean, haven't you ever, someone couldn't get a jar open and they handed it to a person A can't get a jar open, they hand it to person B automatically opens it, and then person A says what? They're like, well, I loosened it for you, right? That's sort of what you can think about jerk is. Jerk is the initial pull on it. And you can also think about jerk when you're driving, okay? If you're accelerating very quickly, okay, so you're in your car and you're accelerating and all of a sudden a coyote runs into the road and you slam on the brakes. So you're changing your acceleration very quickly you're changing your acceleration with respect to time in a very quick manner. That's going to be jerk. And you physically feel it, right? I mean, if that happens, if someone's accelerating and then here comes coyote and they hit the brake, right? Then they're going to jerk. I guess you can hit a coyote, but you don't want to hit like a moose, right? Mooses kill your cars, right? Deer don't do a lot of good things either. Okay, so let's go ahead. Yeah, javelinas aren't great. Neither are armadillos. My husband really screwed up the bottom side of our car hitting an armadillo. Okay, so let's go ahead. You guys don't have your book, but let's go ahead. We're going to want to find velocity and acceleration. All right, and we're given a position vector. And our position vector is then t squared 1 over t squared. All right, and let's also find speed. And we're going to check all of this stuff out at t equals 1. All right. So let's go ahead then and take a peek at this. The velocity, right? I just need to take the derivative of r. Now I'm going to rewrite my r. And hopefully this is intuitive to you guys. It should be at this point in your careers. It seems to be my 212 students that we have to spend extra time talking about turning positive into negative exponents, because they try to take derivatives when it's a 1 over t squared, and then they get all confused. And then of course it's my fault because that's the type of students business students are. And then I get these emails. All right, so this is then 2t negative 2. Now remember, this is then going to be t to the negative 3. All right, so that gives us what? That gives us our velocity vector. All right, so what's happening here? If t equals 1, what are we going to have? We're going to have 2, and then we're going to have negative 2. Since this is 2 dimensions, this isn't too hard, so to speak, right? Our position vector is going to start off here. And then what's going to happen, this is going to be positive x, and that's going to be negative y. So we're going to go over 2 and down 2. So my velocity vector is then going to look like this. All right. We can also figure out our acceleration vector. because that's then going to be the second derivative. So that's going to be 2. And then this is going to become positive 6 t to the negative 4. If we check out what's happening at t equals 1, right, we're at 2, 6. So at t equals 1, right, we're then going to go over 2, except we're going to go up 6. So this is going to be something that looks like that. I'm trying to change color. There we go. Something that looks like that. All right. The speed is then going to be, oh, not v prime. The speed is then going to be the magnitude of v. So that's going to be the square root of 2 squared plus negative 2 squared. So that's the square root of 8. I always write it this way. I'm not sure. I haven't done enough WebAssign problems to see what WebAssign wants you to do. But that's how I always do it. If you leave it as a square root of 8 on an exam, you're not going to lose a ton of points. You should do it though, but you're not going to lose a ton of points. All right. All right, does this make, how are we doing from a logical, sensible standpoint? Is it making sense to you? All right, okay, and this looks like it's a lot easier than the last section, and it really kind of is. The other thing we need to do with this is we need to be able to go backwards. All right, so let's do this example, and this is also in your homework. I'm not sure what number it is though. All right, if you're given a of t, that's sine of ti plus 2 cosine of tj plus 6tk. All right. And then we're given the following information. Right? We're told at when v is 0, that's going to be negative k. And the other piece of information we're given is when r is 0, that's going to be j minus 4k. All right, now to go from, and let me know in the chat, I've got the chat open. If we're going from, are we still writing this down? We good, Hannah? Okay, if we're going from position vector to velocity vector to acceleration vector, tell me in the chat, what do? We take the what? Good. Okay, if we start with position, and I want to go, getting some mixed messages here. If we start with position, and I want to go to velocity, I need to take a derivative. To go from velocity to acceleration, I need to take a derivative again. Okay, so that was the first problem we did. So we take derivatives to be able to move through to figure out where those vectors are. If you think about it, when you take a derivative, you find the what? You find the slope of the tangent line, correct? So you have your position, and then you've got your velocity vector, which is going to then be your tangent vector, and then you have your acceleration vector, which is going to be another tangent vector. All right, if you're going backwards, we're starting with the acceleration, and this is what we're going to do in this problem. To go from the acceleration to the velocity to the position, then we're going to need to do integrals. All right. So on the first problem we did, we took derivatives. The second problem we do, we're going to need to take integrals on this one. Now, are we clear on that? Because things were being posted in the chat. Are we clear? Okay. So if we back up one now, so make sure you have this problem written down. We're going to integrate, but we're also given some information, meaning what? We can find our C's. Okay, so we need to be aware of that yes, we can figure out what's happening with the C's for this one. All right, so let's go ahead and get started. And as I said, this chapter really brings everything together. So this is then going to be what? To find the velocity vector, we're going to have the integral of sine of t dt, that's my I component, plus the integral of 2 cosine of t dt, that's going to be my j component, plus the integral of 6t dt, and that's my k component. All right, so when we do this integral, let's think about what's happening here. We're going to have negative cosine of t, right? But it's going to then have a plus, and we'll call it c sub I. That's my I component. Now remember, I know those of you that are in DiffyQ, you guys just you just throw constants all over the place like it's no one's business. You can't do that with vectors. We got to pay attention to what's happening with vectors. This is then going to be 2 sine of t plus c sub j, that's my j component, plus, and then this is going to be t squared over, well, here, hang on. I'm thinking and talking and writing and all of that's bad. So it's going to be t squared over 2, so that's going to end up then being a 3t squared plus c sub k, right? And that would then be my k component. Now, we have information about this, don't we? Right? We have information about this, and that is the information we're given is the fact that V0 equals negative k. All right, I have to warn you about this because you have to stop here and figure out your C's before you continue any further, or you're going to get yourself really confused. All right. As I said, I know in DiffyQ we just mush C's together, throw them off to the side, and keep going. In this class, we're going to need to stop and figure out our C's. So let's see what happens when we have V sub 0. The I component is going to become what? That's going to become, and I'm just going to break it down this way. The I component is then going to be negative cosine of 0 plus ci. That's then going to equal 0. The reason it equals 0 is because of the information I was given about V naught. K is the only one that has a number in front of it, correct? So this one has to equal 0. For the J component, we're then going to have 2 sine of 0 plus C sub j equals 0. All right. Finally, then, for the K component, we're then going to have 3 times 0 squared plus C. Now, this one isn't going to equal 0, is it? Good, Perla. This one's going to equal -1. All right, by the way, this is going to be what? This is going to be here. This is going to be -1. Cosine of 0 is 1. -1 plus CI equals 0. So CI equals 1. This is just going to be 0 plus CJ equals 0. So CJ equals 0. All right, so let's rewrite now our velocity vector with the appropriate constants plugged in. That's why you need to sort of stop, take a breath, and plug those constants in before you do another integral. So our velocity vector, right, is then going to be 1 minus the cosine of t, right, and that's then going to be I, plus 2 sine of t, that's going to be my j component, plus, and then here I'm going to have 3t squared minus 1, and that's going to be then my k component. All right. Okay, now we want to find our, we're done with the velocity. Now we want to figure out our position. Okay, so how do we move from velocity to position? We're going to do another integral, aren't we? All right, so here's my position, going to be my position. We're then going to have the integral of 1 minus the cosine of t dt, that's my I component, the integral 2 sine of t dt j, and then we're going to have one more component, the integral of 3t squared minus 1 dt, and that's then going to be k. All right, so let's go ahead then and do these integrals. All right, the first one is then going to be what? It's going to be t minus sine of t plus ci. That's my I component. I don't know why these little lines are appearing. All right, minus 2 cosine of t plus c sub j, all right, and then we're going to have plus, and then this is going to be t cubed minus t plus c sub k, k vector. All right, now we have a piece of information. And that's the fact that r sub 0 equals j minus 4k. So we can figure out all of our c's. All right, so let's start with the I component. By the way, I'm looking at the chat, is the I component in the information we are given? Okay, it is indirectly because it's 0, since it's not there. Right, and so that's one of the things you need to look for. Is it 0 because it's not there? All right, so we're going to end up with what? We're going to end up with 0 minus sine of 0, which is 0, plus c sub I equals 0 So C sub I equals 0. That one's done. Now, let's go ahead then and look at the J component. All right, the J component is then going to be -2 cosine of 0, which is going to be 1, plus C equals a +1. It's a +1 because that was given to me in my R0 equation. So this becomes -2 plus C, technically this is C sub j, equals 1. So here C sub j is going to equal 3. Finally, we have the K component. And the K component is then going to be, we're going to have 0 cubed minus, or it's not 0, yeah, 0 cubed minus 0 plus C sub K equals -4. So C sub K equals -4. All right, so let's go ahead then and put in our answer into our vector positions. So this is going to become then t minus sine of t, I vector. You didn't follow k. All right, let's back up. The k value was t cubed minus t plus c sub k, Camillo. All right, and we're looking at what happens at 0. So it becomes 0 cubed minus 0 plus c sub k. It then, R0 was then given to us here as a -4. So that's why we ended up with 0 cubed minus 0, c sub k equals -4. All right. This is then going to be plus, we're then going to end up with 3 minus 2 cosine of tj plus t cubed minus t minus 4k. You guys ready for a snack break? Yeah. Let me then take while you're writing this down, let me take a vote. Exit. Slide. At this point, this is really what you need for 13.4. Would you like to do the football example for 13.4, which is more of a kind of a fun practical example? We're so far behind, I don't know if I care. And it's American football. Or we can dive, and it's just, as I said, it's kind of a practical application example in a weird way. Or we can dive into the 14.1. So I need to know what you would like to do after break. Okay. All right. So I'm going to stop sharing here. And start sharing over here. But yeah, I'm happy to move into that if that's better for you. All right, so take a snack break and go ahead and take your vote and let me know what you want to do when we start up again. And I'm going to, well, I guess I'll just let the recording run because I'll forget to do it. All right, are we ready to get started? Let me know in the chat when we're ready to get started, please. Okay. All right, so it was basically a dead heat. So I'm gonna go ahead and move into 14.1. The reason I asked that question is I know that one of the physics profs does the problem. But if you want, let me know, I can do a quick recording of it, or I got a couple of recordings I didn't do for 142. But I can, it's kind of a fun problem. Okay, but let's go ahead and move into 14.1 and functions of several variables. Okay, all right, so, well, let's skip a couple of slides. So let's just do some quick review and sort of how we're gonna work with this idea of several variables. All right, so we're gonna review back to 151, or I don't know, maybe even earlier. All right, and if you remember, for some reason the screen is picking it up every time I touch. If you remember, all right, we would write things like f of x equals x squared plus 2, or we might write the fact that y equals x squared plus 2. And these were both what? These were both one variable scenarios, and that's really all we've worked with all this time is one variable scenario. All right, and this sort of led to a discussion in office hours, because I did an example in class where I had time being t and another particle time being s. All right, because there were what? There were those were two different scenarios, so those gave us two different variables. If you remember back in 151, x was then considered your independent variable. So a lot of times x was then given to you as time, for example. All right. And the other thing that you might remember was x was then our what? X was then our domain. And this is really what we're going to work on today. And then y was our range. Okay, so that was sort of from a algebra historic standpoint, that's what went on. But we are no longer just working in a two-dimensional type setting. All right, and so what we're now going to look at is we're going to look at when we have a function of three variables. All right, so 3D. Now in 3D, z is usually considered then our dependent variable. X and y are then my independent variables. All right, and so from a notation standpoint, similar to our notation back in 151, we might see something like this. All right. Oh, that doesn't make any sense. Hang on. Let's try that again, folks. Or we might also see something like this. Okay. So do you see how the notation is going to change a little bit for us? It might be a z equals, it might be a f of x comma y equals. Ultimately, what we're going to do as we move through this chapter, because what ends up happening in this chapter, it's like we go back to the beginning, all right? We talk about things graphically and visually and verbally and what that means. And then what do you think we're going to do? We're going to take derivatives, where we're going to take partial derivatives. We're going to then deal with integrals, where we have partial functions and how we're going to integrate those. Right? So that's kind of where we're going. What we've done up to this point is everything we've done, we've said in order to make it working for us, we turn it into a parametric equation. Now we're not. Now we're actually going to work with equations in that XYZ space. All right, so let's go ahead and talk about the domain, because domain used to just be about what? Because this is the big one. Domain used to just be X. Now, our domain is actually a function. And a lot of times, you're going to see that it's a plane. Right? All right, so let's go ahead now. Are we good? We're doing okay? All right. Let's go ahead now and let's actually do an example of this type of a problem. Right? What's weird about these problems is we spent years and years drilling you on interval notation, and now we're going to kind of throw it out the window a little bit. So you've been warned. Okay, so go ahead and write this one down. All right, so let's go ahead and talk about domain. Now, natural log, that raises the signal in our brain, right? The warning signal that there's going to be a problem, correct? All right, so what do we know about natural log that's going to give us a problem? Well, 4 minus x squared minus 4y squared, that has to be greater than 0. Okay, so in order to look for what's going on with our domain, we're going to have to now do some manipulation with this. So if I move the 4 over, I'm going to end up then with negative x squared minus 4y squared is then greater than negative 4. All right. When we divide through by the negative 4, we then see it's going to be x squared over 4 plus y squared over 1 is then going to be greater than or equal to 1.
When you
less than,
divide by an,
is that what you're going to tell me, Hannah? I needed to flip?
yeah, That's what I was going to ask about.
Yeah, no, rules of algebra, still basic rules apply. Okay. Now, we spent some time, 12.6, that's just one of the reasons why we spent time in 12.6. All right, we spent some time doing what? We spent some time remembering what those shapes look like. Okay, and so what is this particular shape going to look like? It's going to look like what? Good, Hannah's got it. It's going to look like an ellipse. All right. So it then asks us, the question says to sketch the domain. Yours, of course, will be multiple choice when you do your homework. All right, but this is then going to be what? It's going to be plus or minus 2. That's going to be my major axis. 1 is going to be my minor axis. So we're going to get an ellipse that looks like this. All right. Now, why is that a dotted line? And this is where WebAssign tries to trick you up. Why is that a dotted line?
Because it is not equal to?
Right, it's not equal to. It is not on the line. It is not included. All right, but then the domain is then everything in here. So we can think of the domain then from sort of an algebraic standpoint is then 0 to plus or minus 1 and plus or minus 2 to 0. All right, we can also write down the range for this problem, can't we? It's not asking about range, but since we used to do it, let's go ahead and figure it out, right? The range is then going to be what? It's then going to be, it cannot actually be 0, but then in theory it could run to infinity. I know it went away. It's back. All right, are we good to move on to the next problem?
No, I'm sorry, I didn't catch. Why is the range going to from 0 to infinity? Sorry.
No, that's fine. Because if you think about it, this function here, Perla, that's what gives us our range. Okay, it's not ever going to be 0 because it's a natural log, but then it could be anything after that. Okay, so when you're looking at range, you're actually looking at what happens with this natural log component. All right, and if you remember our 3 big issues, and I have 2 of the 3 prepped. Do I have 3 of the 3 prepped? No, I don't. All right, but I do have 2 of the 3 prepped. So the 2 out of the 3 is what? Rational functions and square roots and natural logs. That's where we're going to run into domain issues. The rest of the time, everything can be good. All right, so let's go ahead then and look at one, as I mentioned, all right, where we have something like this.
That's a 1 minus x squared, correct?
Correct.
Thank you.
Okay, so let's go ahead and look at what's going to happen for the domain on this one, right? 2 variable domain has an x and a y scenario going on. The top has a problem, correct? So the problem on the top is the fact that this has to be 2 minus x has to be greater than 0. Right? I can move the x over, so 2 has to be, so x has to be greater than 0. All right, we all agree that's what's going on the top? All right, let's then check out what's going on the bottom. Now, the bottom can't be 0 either because it's a rational function, correct? And so the bottom is then going to be, let's see, we're going to have 1 minus x squared minus y squared. This then cannot equal 0. All right, so we can then write the fact, and I'm just going to figure out what's going on with x squared and y squared. So x squared plus y squared, right, equals 1. It really can't equal 1. That's the problem we have with this, correct? All right, so let's talk about how we would make this look. Now, one of the things I think you remembered, right, was that, and I don't know, maybe not, but that when we're dealing with domain, with complex, no, it wasn't called, was it called complex functions? I can't remember now. When we were dealing with those, right, it's like the domain, the worst domain wins, so to speak. So here we are at x equals 2, and we know that we have to be less than that. So we're going to be everything less than this, but we're going to then have what going on here, here, here. We're going to have a circle, and let's not make it a solid line, right? There's going to be a circle in here where the numbers cannot work. All right. It wouldn't really be a hole. It would be more like a donut, a very, very skinny donut. Okay, because Dacia, stuff on the inside can be true. Like I could have x equals 0, that works. All right, but yeah, so it would be more like a donut than a hole. All right. All right, I think we're not going to do problem 18 because we need to get into discussing contours. Oh, we just did problem 18. So we're ahead of ourselves. All right, let's go ahead and just quickly review how we sketch these graphs of a function when we're dealing with things in 3D. So you're told to sketch this graph and you're given, that's lame. Come on, be an eraser. Goodness, the board is not cooperating. I'm actually moving too quick. I need to slow down.
I have a question, Dr. Mickey.
Go ahead, Joe.
Can you give us the notation for the domain there? Are we subtracting that function out of there?
So the notation for
the
domain would be a two-part notation. Part of it would be that x is less than 2, and the other part would be x squared plus y squared does not equal 1.
Oh, that's it. Okay.
Mm-hmm. All right. Okay, so let's go ahead and talk about graphing these functions. Now, this one is an f of x, so we're really going to look at this and graph this like that. Okay. And so what is this then going to look like? Now, I did this on the very first slide. You can think of this as your f of x, y, your dependent variables. We can think of that as just being z. All right. And so what happens with this? Well, I'm an intercept graphing type of person. All right, so let's go ahead and put in 0, 0. I'm just putting in points. You can put in random points, but let's put in 0, 0. And then what comes out is then 8. So if I put 0 in for x and 0 in for y, all right, what comes out is going to be 8. So that's hanging out there. All right, if we think about it, if we put in a 0 for x, and I say I'm going to put in a z for 0, 0 for z, what's going on here, right? I'm going to end up with -8 equals -2x. I move the 8 over because I put the zeros in. Or, I'm sorry, y. And so what I did, and we do this in graphing all the time, all right, is I said I'm going to make x equals 0 and I'm going to make z equals 0. All right, don't we do that all the time? If you were working with someone who's in a college algebra class, what would you tell them to do? You would say make x something, solve for y, correct? Well, we're doing a similar type situation here. If we do this, then y equals 2. So we're here. Okay, finally, let's get our intercept on our x-axis. So we're going to say y equals 0 and z equals 0. I'm going to plug that back into my equation. So I end up then with 0 equals 8 minus 2x. -8 then equals minus 2x. So x then equals 4. We get something that looks like that. That would be a plane that would keep going, wouldn't it? You'll see how that would just be a plane. Okay, in addition, let's back up and talk about this. What about my domain? Would I have any domain issues on this? No. So everything would be good. All right, where do we use this? Okay, where is this going to become important? And hang on. All right, let's go ahead and look at this. All right. This is a what, folks? If you've ever been hiking, you know that this is a contour map, correct? All right, and what you're going to see All right, and so what you're going to see is you're going to see things that are going to say like, let's go ahead and do, what is the slope change? Well, let me back up before we actually do a question. All right, let's talk about what this is showing us. Now, if you hike or you off-road or something, you've seen these quite a bit. These are contour maps. If you don't, you're going to see them anyway, because, and my husband actually had one of these up the other day. They also, a lot of times in a lot of materials, they use these as temperature sensing maps, right? So they have a whole bunch of temperature sensors on it. And so you can think about the temperature is changing in the Y or the Z direction, all right? So if you have a plate and then you've got your temperature. And so let's talk about how to read these, right? And these little points here, these are elevation. Sorry, spelling is a new technique. All right, and so this is my coordinate system from the east, and then here is my coordinate system from the north. All right, now I actually had to take mapping. I don't know why. I had to take mapping when I was in college. I hated it, but it is very helpful. Right? This would in essence be the top. And you can see if we look at these elevation contours, they go 8.34, 8.36, 8.83.8, 8.83.4. All right, so we can ask ourselves questions about this type of scenario and these types of contours. All right, if I want, for example, to go, let's see, let's figure out the elevation change. I need to pop open my tea thermos. All right, let's check out the elevation change from, and let's use the coordinate -32, 29. All right, and let's look at another coordinate that's -29 to -28. -29, comma, -28. Okay, now these are what? You can think of these are my XY coordinates. All right, here we can think of this as X and our Y coordinate system. And as I said, this one is a topographical map because they're easy to find online, so it's elevation. It could also be temperature, couldn't it? What's the temperature gradient? That's what you're going to hear. You're going to hear the word gradient. All right, so in your homework, you're going to have to interpret these maps. So let's go ahead and look at -32.29, -32.29. All right, I'm going to rough it out. You can use it to take averages, but we're going to say that's awful close to this elevation. All right, if this is 2.836 and that's 2.838, I'm going to estimate that I'm looking at about 2.837. So my elevation on this one's going to be 283.7. All right, now, where did that come from? That came from, I'm not quite at 283.8. All right. Okay, let's then look at the elevation for the next one, which I said was going to be at 29 and 28. So we're coming here to 29, and then we're coming over here from 28. Hang on, that is by no stretch of the imagination a straight line. Okay, that's disappointing. I was hoping it would land on the top. Okay, so that is, let's see, this is 284.0. We're a little higher than that. If we look at these are going, let's see, 0.6, and then we go to 0.8, so that's about 0.7. We go 0.8, 0.9. So this one here is then going to be 2.841. I'm not sure if you saw how I did that. 284.1. All right, so we're then about halfway between those two. So we'll call it 284.05. All right, so let me back up and show you what I realized was going on with these elevation curves, because I'm worried I've lost a couple of you. This was 283.6. So the one right next above it is then going to be 283.7. The next one is then 283.8. All right, that's how the lines are drawn on the map. So if we're looking at our elevation change between these two, what are we going to do? Okay, we're going to look at the delta between them. So you're then going to take 284.05 minus 3-minute warning, 283.7. I don't have a calculator out. Okay. All right. Now, these get much more interesting when they're actual contour maps in 3D. Don't know if I have, and we've got to figure out where things are going from there. In application problems, typically a lot of times deal with temperature. Thank you, Skylar. 0.35. And I'm in meters. So between those two elevations, I'm going to climb 0.35 meters. Okay. We will wrap up 4.1. So you need to finish chapter 3 by midnight on Sunday, right? 3.3 and 3.4. And then we'll wrap up 4.1. I know we're way behind. It does kind of stress me out, but there's some optional topics in there we can bail on, and I'll alter the test. So wherever we end is then that on that Wednesday, October 7th, that will then be the last material required on your test. If I have to split chapter 14, it's not a crisis.
Hey, Dr.
2 homeworks and 2 quizzes. 3.3, 3.4. Let me write it down. All right. 3.3 and 3.4. Homework and quizzes.
13.3 and 13.4.
Oh, yeah, that would make a lot more sense, wouldn't it? I remembered the last 2 parts of it. Don't worry about 14.1. Yeah, you guys can go back and do 3.3 and 3.4. Back to a Calc 1 experience.
Hey, Dr. Minky? Hello?
Ethan, are you talking to me?
Yeah, I'm trying to. Can you hear me?
Yeah, now I can. Go ahead.
For the exam, since we've like covered so much material so far, what really should we like be expecting for the exam as far as like length, like how much, like how many questions or like how much material, I guess. I mean, because
Well, you'll expect a lot of, the best way you can figure out what's going to go on the exam, no, there's no either. The best way you can figure out what's going to go on the exam, and I think I mentioned this earlier, is if you go to WebAssign and you scroll all the way down, you will see it say, yeah, I'll get the extra credit in there. You scroll all for number, what was it, 8 or something. You scroll all the way down and you'll see their practice exams in WebAssign, and that'll give you the best idea.
I'm sorry.
So if you go to WebAssign and you scroll all the way down, if you hit more and then you scroll all the way down to the bottom of the assignments, you will see the practice exams for exam 1, exam 2, right? We might not cover all the material, so I'll cut that material off. There's a lot of material in this class. There's no other way around it.
I got you.
All right, guys, I'm gonna have to go open the other classroom. So thank you for joining. I'll have to look, Eric, to see how many questions are on the exam. Can you send me an email asking me that and I'll look that up? All right, guys, have a wonderful day.